Hi, and welcome to Eng Phys 3004 Lectures 16 and 17, where we're going to look at Chapter 18, Transient Heat Conduction. First, 18.1 is going to look at situations where the whole object is at the same temperature at any given time. So the temperature is only a function of time rather than time and space. Then 18.2 and 3 are going to look at special cases, so really special geometries for objects that are changing temperature, and we're going to look at how the temperature changes with space and time for those special geometries. Then, although they're kind of limited in 18.4, we're going to learn how to combine those geometries to make a much larger set of geometries. Everything that we're dealing with in this chapter is going to be taking the assumption of uniform convection at the surface of an object, so same convection coefficient everywhere at the surface, and an initial temperature distribution which is uniform, so same temperature everywhere, at least initially. Okay, first section, 18.1, lumped system analysis. Again, this is going to be valid if the temperature of the object is all uniform, and that's going to be a good approximation if the resistance to conduction through the object is much lower than the resistance to convection at the surface. So generally we'll define resistance for conduction through the object as using the surface area of the object and the length scale, characteristic length of resistance to conduction in the object, which is just it's an arbitrary length, not really defined from a specific spot like the center to the edge or something, because not all of the heat is going from exactly the center to the edge. And characteristic length is defined then as the ratio of the volume to the surface area. So this is going to be appropriate for determining whether the conduction is a limiting case or not. So generally resistance to conduction through the object is going to be based on that length scale, volume to surface area, divided by the area. Now here we use surface area again, times the thermal conductivity of the object. So that's your resistance to conduction of the object, similar to the plane wall formula, except using the characteristic length and the surface area of the object. And resistance to convection, this is more standard. This is happening at the surface, so you would just use 1 over h times the surface area. Working all of this out, you can define this ratio, the BO number, as h LC over K, where LC again is this ratio of volume to surface area, the characteristic length. If the BO number is less than about 0.1, then we're going to say this analysis is more or less justified. To recap then, low BO number means that conduction is very fast compared to convection, and the object is mostly at a uniform temperature. Therefore, you can use this lumped system analysis we're going to derive soon. That would be valid for a small copper ball, whereas high BO number would mean that the temperature is changing appreciably within the object with space, and that might be true for a large roast beef, something like that, which means that this next analysis, lumped system analysis, is not valid because the conduction has an appreciable resistance compared to the convection at the surface. All right, so let's suppose that lumped system analysis is valid. Then you can say that the rate of change of the energy of the system is equal to the rate of heat flow into the system. So the heat flowing into the system must change its energy. That's true all the time. The value of doing this for lumped system analysis is that now we can write out what all these things are and solve for what the temperature must be as a function of time. So the heat flow into the system by convection is HA, the temperature of the fluid free stream, minus the temperature of the surface of the object, and the rate of change of energy of the system would be the time derivative of mass times specific heat times the temperature. Since the temperature is uniform within the object, this is not a function of space, and we can use the same temperature as we used at the surface. This is then a first-order differential equation, which you can solve by separating and integrating to get that the temperature is related to the initial temperature of the object, the free stream temperature of the fluid, and decays from the initial temperature towards the free stream temperature according to an exponential function with a time constant of B is convection coefficient times surface area divided by the mass times specific heat. Substituting in the density and the volume, you can redefine this in terms of the characteristic length if you like. Now this time constant is multiplied by time rather than being the thing that you divide the time by. So not like a tau from electronics or anything like that. This means that it has a dimension of inverse time rather than time as is typical. Either way, it still is a decaying exponential function just like we're used to seeing for this sort of thing. And this is the result that would be quite easy to use as long as lumped system analysis is valid. So you can, even if it's not valid, use lumped system analysis as a quick check and initial calculation of what the temperature should be changing like in time. If we have resistance within the object being appreciable, so the temperature from the at the center can't change initially, it has to be limited by heat flow from the center towards the edge first, then you can see that that would probably slow things down. So lumped system analysis will give you overestimates in how much the temperature has changed of the object at any given time. Now on to the actual transient heat conduction. First special geometry case is going to be large plane walls, long cylinders, and spheres with spatial effects. And then in 18.3, we're going to look at semi-infinite solids. So first off, large plane walls, long cylinders, and spheres. So in general, temperature changes with time and space according to the heat equation. Heat equation tells you that rho Cp, so density times specific heat, times the time derivative of the temperature at any given point, minus the divergence of the conductivity times the gradient of the temperature, is equal to the rate of volumetric heat generation within the object. Now, in detail, for a specific geometry that you're interested in, you could solve this using finite element method. So basically do some computer simulations in order to figure out what the temperature is changing like with position and time. And that would be doable pretty much for any geometry, any boundary condition set, any initial temperature distribution, any rate of volumetric heat generation inside the object that you like. Although it's in principle doable, it could be in practice quite difficult for you to actually set all of that up. Finite element method can handle that. But for a limited set of geometries and initial conditions, we can actually solve this analytically, and that's what we're going to do in this section. So this will be fun. It'll enhance our math skill. We'll get a feeling for how the transient heat flow works, and then we can extend that to real geometries, and we'll even learn how to extend it to deal with a larger set of geometries in 18.4. All right, so first off, what we're going to be dealing with is no heat generation and constant conductivity. So K is a constant, and there's no internal heat generation. Then the heat equation will turn into this form. So divergence of the gradient is this del squared operator, and then we have 1 over alpha thermal diffusivity as defined earlier, times the rate of change of the temperature at any point. In one dimension, this would turn into just a second derivative with respect to space, so with respect to your maybe position inside the object on the left. All right, so first off, we're going to deal with the large plane wall, and here's our geometry set up for this problem. A large plane wall, so it's infinite in the vertical direction here and infinite in and out of the page. We only have temperature changing in one dimension then, and we've got the same convection coefficient on each side, h. The length from the center to the edge is defined as L. So L is not the thickness of the wall. 2L is actually the thickness of the wall. L is from 0 to the edge. Okay, so to solve this, the first thing we're going to do is to non-dimensionalize the differential equation. Prior to that, let's just re-examine what we've got, the differential equation that we mentioned earlier. The boundary values of this would be, first of all, symmetric temperature across the center. We've got to have that the temperature because of this initial setup, same convection on each side, there's no reason the temperature should be higher on the right side than the left. And in fact, at the center, we've got to have a symmetric temperature distribution, which means the slope of the temperature at the center has to be 0. Then we've got that at the edge, we have conduction heat flow matching convection heat flow. So the temperature, the heat can't build up at any infinitesimal point either. Okay, so that means that negative K del T by del X, this is the conduction heat flow per unit area at the edge. So at X equals L anytime has to equal the convection heat flow there. So H times the temperature at that spot at LT minus T infinity. This would be the convection heat flow out of the wall and the conduction heat flow out of the wall as well. They must match. Okay, and initial value is that the temperature is a uniform Ti everywhere. This is kind of limiting, but still is going to let us solve a number of different problems. So maybe you've got some really hot plate coming out of an oven. It's basically all at the same temperature, and let's look at how the temperature changes with time. Again, the first thing we're going to do is non-dimensionalize it. This is a pretty standard thing to do in physics and especially in fluid mechanics. So the dimensionless temperature that we're going to define is called theta, and this is defined as the temperature minus the free stream temperature divided by the initial temperature minus the free stream temperature. And we're going to define dimensionless position as the position relative to the length from the center to the edge of the wall. After you substitute these parameters in, the differential equation turns into this. So it becomes del squared theta by del dimensionless position squared is equal to L squared over alpha del theta by del time. We also want to define a dimensionless time. Now that we've substituted this in, we can see that a good choice to use for dimensionless time is tau is alpha over L squared t, so that when we substitute that in, the entire differential equation is just del squared theta by del x squared equals del theta by del tau. Tau, this dimensionless time definition, is also called the Fourier number. This is going to be an important characteristic that, by looking at it, tells you basically the rate of heat conducted to heat stored at any moment. As time goes on, then you have a higher ratio of heat being conducted through the object to heat being stored at any position. The boundary conditions, after substituting in these dimensionless numbers in place of the previous dimensioned variables, become symmetric about the center is pretty much the same as before, del theta by del x at 0 and tau is 0. Convection heat transfer at the wall surface turns into that del theta by del x at 1 and tau. So previously we had that this was at little x is equal to L, is at dimensionless x is equal to 1. Now the other side of this turns into HL over K, which, hey, that was just the BO number from the last section, times theta at 1 tau. Okay, and the initial value, temperature initially is Ti. If you look at our theta definition, when temperature is Ti, that means theta is equal to 1. So that tells you theta at x and time 0 is 1. All right, so this setup, with the dimensionless temperature, dimensionless position defined like that, we've got and dimensionless time defined as given there, gives us this problem. So this differential equation subject to these two boundary conditions and this initial condition. BO number is a positive constant. So basically, for any plane wall, we've got a solution that, rather than possibly being a different solution depending on what L was, what K was, what H was, and what Ti was, the differential equation is now only going to depend on the BO number. So we'll have the same solution versus x and tau depending only on the BO number. That's kind of amazing. So this lets us solve it only once for every different BO number, and then find out how this changes as a, and then just apply that solution to a number of different problems, a number of different L's, TI's, etc. So if you want, you can now go about solving this problem yourself using a separable solution assumption, the same kind of stuff you probably did in a second-year partial differential equations math course section. Let's just jump ahead to that and overview it briefly. Essentially what you do is you substitute in a separable solution, so you assume that theta is a function of only your, that theta itself, which is a function of dimensionless position and time, is actually a product of a function of only dimensionless position and another function of only dimensionless time. After you do this, then you can substitute this definition in for theta, and that allows you to separate the separate functions here, u and v, onto different sides of the equation. Now, since u was only a function of position and v was only a function of time, that means that the left-hand side has no time in it and therefore is independent of time. And the right-hand side has no position in it and therefore is independent of position. But if the left-hand side is independent of time, then so must the right side be. So even though v prime and v themselves are functions of time, this ratio is not. Same thing for the left side with a function of position. Since this isn't a function of position, this can't be either. So that means both sides have to be independent of position and time, and therefore are equal to a constant, which we're going to call, with a little bit of foresight, negative lambda squared. So we're assuming that the constant is a negative number. By substituting, by this assumption, we can then solve two different ODEs. So u double prime equals negative lambda squared u, which gives you your trig functions, and v prime is negative lambda squared v, which is a decaying exponential. So if we now apply the boundary conditions, so del theta at 0 tau by del x equals 0, which is u prime at 0 times v at tau. If we want non-trivial solutions, we don't want to assume that this is 0 because v is 0 everywhere, so we'll just take u prime at 0 is 0, which, looking up at what our u solution was, tells you that c2 is equal to 0, so now you've got that u is just equal to c1 cos of lambda x. Now this next condition gets a little bit hairy compared to what would have happened in a second-year differential equations course most of the time, which is after you substitute in del theta at 1 by del x is equal to negative BO number theta at 1, then we come up with negative lambda sine lambda equals negative BO number times cos lambda, or in other words, lambda tan lambda is the BO number. So this still has infinite roots, but they're not exactly evenly spaced, and it's not easy to write out a simple formula for what lambda is. If you had enough time and a numeric solver or just a plotting program, then you could find out any root that you liked from this, but we'll just say that lambda tan lambda is equal to the BO number. So anyway, there's an infinite number of roots, lambda 1, 2, 3, 4, etc. And that means that we found an infinite number of solutions so far that satisfy the differential equation and that satisfy the boundary conditions. We haven't applied the initial condition yet. To be able to satisfy the initial condition, let's form a general solution by saying that, hey, this differential equation was linear, therefore a linear combination of solutions is also a solution to the differential equation. So the most general thing that we found from this separable assumption was this linear combination of all of the different cosine times an exponential solutions. Okay, so to recap, we've got that we can satisfy the DE and the boundary conditions with an arbitrary linear combination of theta n, where theta n is cos of lambda n x e to the negative lambda n squared tau, where lambda n are the roots of lambda tan lambda is the Biot number. So the only parameter that this depends on, as promised, is the Biot number, and it satisfies everything except the initial condition so far. To satisfy the initial condition, we can substitute this into this assumed, this solution form that we've come up with into the initial condition, and we get theta at x0 is equal to 1, which would be the sum of just the cosines, not the exponential. That gets terminated by substituting in tau is 0. All right, now if we had evenly spaced lambdas, then this would be a Fourier series, and then you can guarantee that the terms are orthogonal so that you can determine what the CNs are. Now, with this setup, with the lambda n's not being evenly spaced, it's not a Fourier series, but it still might be orthogonal with respect to some weight function. And even if it's not orthogonal, you can say that this is a linearly independent set of functions. So it must form a basis for all function space. So in general, you can expect that there must be some solution to this, some set of CNs that will solve this, that will satisfy this equation. It turns out that the CNs that work are 4 sine lambda n over 2 lambda n plus sine of 2 lambda n. Okay, so that is to say that the sum of 4 sine lambda n over 2 lambda n plus sine 2 lambda n times cos lambda n x for n equals 1 to infinity equals 1 for any value of x as long as lambda n times tan lambda n is equal to the Biot number for all of the lambdas. Okay, so to recap, what we found is that for the infinite plane wall, the solution is the sum from n equals 1 to infinity of 4 sine lambda n over 2 lambda n plus sine 2 lambda n times e to the negative lambda n squared tau times cos of lambda n x, where lambda n are the roots of lambda n tan lambda n equals the Biot number. All right, so we did this for the plane wall. If you had done it for the long cylinder, then you would have had a similar kind of a solution process, except that now instead of the sine functions, you end up with Bessel functions in this setup, and the roots are also defined in terms of this Bessel function ratio. If you're not familiar with the Bessel function, it's another set of perfectly well-behaved functions. So we're looking at the Bessel J functions. These are called the zeroth and first order Bessel functions of the first kind, and they're defined by this by series, depending on what order they are, where again this definition might involve another function you're not familiar with, which is the gamma function. Gamma function is like a factorial as long as you give it an integer. So gamma at z is z minus 1 factorial. It's also defined at non-integer values though. So here we have Bessel functions. The zeroth order Bessel function of the first kind is this thing in red here, and you see it has a number of roots. So it's kind of like a cosine in that at 0 it's 1, whereas the first order Bessel function of the first kind is the one in green, and this is in a way like a sine function because it starts at 0 initially. All right, so they're periodic. Well, I guess they're not quite periodic, but they have an infinite number of roots as their argument goes to infinity, and that's good enough for us for this purpose. So, although these full series are the actual answers, you'll notice that they have this decaying exponential term that goes like lambda squared times tau. Given what the values of lambda end up being, depending on the Biot number here, for most cases, it turns out that you only need the first term of the series. So you can use a one-term approximation to get a much easier to deal with answer. So for the plane wall, it ends up being a constant times e to the negative lambda 1 squared tau, cos of lambda 1 times dimensionless space. For the cylinder, it's the same kind of thing except with a zeroth order Bessel function of the first kind. And for the sphere, it's the same thing, but now multiplied by what you may call a sinc function, sine of lambda 1 r over r naught over lambda 1 r over r naught. Now, there's a convenient table in the book that shows you what the coefficients are in front of these one-term approximations and what the first root of the generating functions are for each of these approximations as well, depending on which BO number you're dealing with. There's also a table if you're using the cylinder approximation, which is quite a common shape, to give you the Bessel functions, because you're also going to need to evaluate these in order to determine what the temperature distribution is doing as a function of space. So you only need the 0th order Bessel function of the first kind for the temperature distribution, but we'll need the first order Bessel function of the first kind for another thing that we want to get from this, which is the ratio of the heat dissipated to the total heat that will eventually dissipate. So let's talk about this. After a long enough time, the heat that has transferred from, let's see, so we've got MCP T infinity minus Ti. This is looking at the rate, the heat transfer if T infinity is higher than Ti. So this is the heat transfer to the object. The total heat that will transfer to the object is MCP T infinity minus Ti. That's if you wait long enough when the object has changed its temperature from Ti to T infinity, the free stream temperature. At any point, the fraction of this heat that's transferred is the integral of temperature minus the initial temperature times rho Cp with respect to volume divided by, again, Q max here. So that would be the heat that's transferred at any given time and the heat that will eventually transfer. So this ratio, after working some things out, would be non-dimensionalizable into the integral with respect to volume of 1 minus theta divided by the volume of the object. So if you substitute the one-term temperature distributions into this, then after a little bit of manipulation, it turns out that you get 1 minus the temperature at the center of the wall. So this is the center line temperature times sine lambda 1 over lambda 1 for the wall, 1 minus 2 center line temperature of the cylinder times the first order Bessel function of the first kind at lambda 1 over lambda 1. And for the sphere, same kind of a formula, but with a 3, and sine lambda 1 minus lambda 1 cos lambda 1 over lambda 1. Again, remember that the lambdas that you use depend on which temperature distribution you're talking about. So the lambdas for the wall are not the same as the lambdas for the cylinder, even though they all have the subscript lambda 1. Even these one-term approximations can be kind of difficult to use, so it's you have another option which can potentially be faster, although a little bit less accurate, a little bit difficult to read, and that's the Hessler charts. So these are, yes, they're kind of difficult to read, but they're typically faster once you get the hang of them than using the one-term approximations, although they're probably not going to be quite as accurate as those. So here's how they work. There's a series of 3 different charts. First one will tell you what the midline temperature is. So for plane surfaces, this set of charts, there's a different set of charts for cylinders and a different one for spheres. Anyway, looking at the plane surface ones, the first plot will tell you what the temperature is at the center of the plane walls as a function of BO number and Fourier number. So if you have a BO number of, let's say, 0.2, then 1 over the BO number would be 5. So you know that you're dealing with this line there, if I can trace it right. Yeah, I think it's this one that goes up to the top there. And on here, sort of scales down. It looks like it hits 0.001 at, looks like 30. So that, what's the scale here? 30. Then we've got 1, 2, 3, 4 divisions to get to 50. So that must be 30, 35, 40, 45, 50. This is a linear scale here, and it's a linear scale here, although the scale is different. So that way it accomplishes something like what a log plot would do, where you can zoom in on details where things are changing quickly and then zoom out where they're changing a little bit more slowly, but you can also read the scales within any one of the sections like you would linearly. So like we did there with this 30, that 50, and the number of divisions tells us the divisions here are units of 5, whereas over here the divisions are units of 2. Here the divisions are units of, looks like 0.2. Okay, so anyway, the 1 over the BO number equaling 5 intersecting 0.001 at tau equals 37 or so tells you that once the Fourier number is 37 for a BO number of 0.2, the midline of the infinite plane wall will have reached to within 0.001 of the free stream temperature. Okay, so you could figure out what the midline is as a function of BO number and Fourier number, no matter which BO number and Fourier number you're dealing with, although this does become a little bit difficult to read for these low Fourier numbers. So that's very soon after the temperature has started changing. Once you've got the midline temperature, you can use the second Hessler chart to find out what the temperature is at some other value. So x over L, this is your dimensionless position. X over L is 0.2. That would be close to the center. X over L is 1, would be right at the edge. So what the temperature is relative to the midline temperature. If temperature relative to the midline temperature is low, that means we're closer to the free stream temperature. If temperature relative to the midline temperature is high, so 1, then it means that you're closer to the midline. And that's not surprising. As you go up to these lower dimensionless space values, you get to higher numbers, which are closer to the midline. Now look at this. As 1 over the BO number goes up, the temperature elsewhere becomes closer to the midline temperature. Well, okay, so we remember that low BO number means the object is all basically at the same temperature and most of the resistance is to convection at the surface. So low BO number would mean that 1 over the BO number is high, and that's then what you would expect. All of the lines kind of converge if you're dealing with a low BO number, because the entire object is more or less at the same temperature. Whereas over here, where 1 over the BO number is small, that means the BO number is high, so there's a lot of resistance to conduction inside the surface compared to convection at the surface. So inside the surface, I guess I should say, inside the object. And that means you can have a pretty different temperature at the edge than you would have at the center. Finally, the last Hessler chart is this fraction of total heat transferred versus time. So this is the one that gives you the Q ratio that we dealt with here for the one-term approximation. So fraction of total heat transferred versus time can vary from 0 initially to 100% after a long enough time. Now how long this takes depends on the BO number, depends on the BO number squared times the Fourier number. So for any BO number, as you increase the Fourier number, you move to the right on this plot, and that leads to more and more of the heat transferred. That makes sense? How does this work with BO number? If BO number is low, then you would be dealing with one of these lower charts over here. Now, low BO number means that the object is all more or less at the same temperature, and that's kind of the lumped system approach being valid. So, but what does that mean over for this chart? If BO number is 0.001, then you're going to need a higher Fourier number to be over this far in the first place. So it's a little bit complicated and counterintuitive, but you can substitute in some values here to see how BO number squared times Fourier number works, and that's h squared alpha t over k squared. So still depends on h over k and alpha, and as time increases you move to the right along any one of the plots that you're dealing with. So while the charts can be a little bit complicated to use, ultimately you just need to know the BO number and Fourier number and position that you're interested in, and then you can find out what the temperature is. and what fraction of the total heat has transferred from the object. Remember that if you're dealing with cylinders, you need to use a separate set of charts, but they work exactly the same. And same thing if you're dealing with spheres, separate set of charts, but they work the same. Also recall that the Fourier number we said was the ratio of the heat conducted to heat stored. So that kind of makes sense. As time increases, less and less of the heat is stored in any given spot, and more of it is conducted through. Temperature profiles that we found for these different shapes, so say the infinite plane wall, depend on what's going on at the surface versus inside the object. So here is what a typical temperature profile would do. If you've got infinite convection, so as the convection coefficient goes to infinity, then what we end up with is kind of a still reasonable shape inside the object, but pins to a sharp transition right at the edge because the convection is dominating. So that's pretty much what you would expect to. Okay, so now let's learn how to deal with something different, which is an infinite solid, really a semi-infinite solid. So this would be something which is infinite in one dimension. Maybe you're close to the surface of the Earth and you say, well, this is basically infinitely deep and infinite in the other two dimensions as well. So the temperature as we go infinitely deep into the object is not going to be changing. Before we deal with this, we're going to need to know what the error function is. So 2 over root pi times the integral of e to the negative u squared du from 0 to eta is defined as the error function at eta. So eta is how far we are integrating e to the negative u squared du. The error function limits to 1 pretty quickly. So after 2, you can see that we're basically all the way there. Between 0 and 2, it's changing a fair bit quickly. So here we've got the error function in red, and the complementary error function defined as 1 minus the error function is plotted in green. That starts at 1 and then decays down to 0 reasonably quickly. So here's some tables, 18.4 of the error function and complementary error function. You're going to need that because this is the result of the temperature distribution in the semi-infinite solid. So the results depend on what surface boundary condition you're talking about. If you've got a constant surface temperature, it turns out it's the error function times the complementary error function of position, so depth into the object over root 4 alpha t. If you've got constant surface heat flux, then another formula, but again still involving these error functions. Convection at the surface, probably the most common case, is error function, so complementary error function I should say, at x over root 4 alpha t minus this exponential term times erfc of x over root 4 alpha t plus h root alpha t over k. And another result for an energy pulse at the surface. This is a finite amount of energy delivered to the surface that then decays away in time. So all of these different surface conditions are ways to deal with the semi-infinite solid. The way to solve this is a different kind of non-dimensionalizing. So the temperature non-dimensionalizing works pretty much the same as it did before. Temperature is now, though, the difference is instead of involving the T infinite, so the free stream temperature, these temperature functions have involve the difference in temperature from T initial. So we've got a slightly different definition of our temperature. And the other thing is that there's no specific length scale to use for defining the dimensionless space. And because of the different boundary condition 1 is that the solid's infinitely huge. So as you move into the object, the temperature can't be changing at a far enough depth. So no matter how much time you wait, as you move towards the center of the Earth, it's not changing by the situation that's going on at the surface. Okay, so you can solve this but not using the same way that we did before. The way is to define a similarity variable, eta. After you substitute this into the differential equation, it turns it into an ODE in del t by del eta, which is first order. So you separate and integrate to get what del t by del eta is, and then that means that temperature is the integral of this thing, which is why these error functions get introduced, because we end up with an integral of negative e to the negative u squared du. Okay, so here's some plots for the different boundary conditions. So if you've got a specified surface temperature, then as you increase time, this starts to influence what's going on deeper inside the object more and more. With a specified surface heat flux, that's a specific rate of heat going in at the surface, the plots look a little bit different. Then convection at the surface, probably the most common case, and the energy pulse, this is kind of penetrating deeper into the surface, but there's the same amount of energy under all of these different plots. If you have contact between two semi-infinite solids, which is a good approximation if two things come into contact and you're looking at very short amount of time, which is not exactly covered by the previous setup, then we've got that the heat flux has to balance at the surface. So if two semi-infinite solids initially at different temperatures are brought into conduction contact with negligible contact resistance, of course, then the interface temperature will initially and always be a balance between the two that depends on their relative conductivity, density, and specific heat. So to get this proof, you set that the heat flow from one by conduction is equal to the heat flow into the other by conduction. Now, the heat flows inside each object depend on their specific properties. After equating everything, then you end up with this temperature distribution and then the surface temperature depending on this ratio of properties. So it depends on the initial temperatures of A and B and the properties of A and B. Last thing for today is kind of short to explain, but very deep in its application. So it's how you extend these previous infinite object results to deal with finite objects. It turns out that if you have a cylinder here, which has heat conduction from the heat convection from the tops as well as from the sides, so it's a finite length cylinder rather than the infinite length cylinder, then you can treat it like the superposition of the results for the plane wall that we had and the results for the long cylinder. So product superposition would tell you that the temperature distribution as a function of time and space, depending both on R and X, would be just the product of the plane wall version, depending on X, and the infinite cylinder version depending on R. So the basic idea behind this is that if temperature is changing from conduction out the sides and out the top, then you just combine the results for conduction out the sides and conduction out the top. Because the dimensionless temperature scales between 0 and 1, this is not going to give you something like a temperature lower than the free stream by multiplying by these two. Yeah, or at least outside the range of initial and free stream. So it's still going to be between 0 and 1, and it's going to be closer to the free stream than it would have been for either the infinite cylinder or the plane wall alone, because you've got more conduction options. For the amount of heat flow, this basically is the same kind of a combination formula, but we have to get rid of double counting. So the fraction of heat that's flowed out is the heat that would have flowed out from the, let's say, plane wall, plus the heat that flowed out from the cylinder, multiplied by the heat that was left over that didn't flow out from the plane wall. So you have to not just add the total heat together, that would be double counting for parts of the area. So you've got to modulate the second one by what's left over that didn't flow out from the first shape. For three bodies, you do the same thing, but then when you add in the third one, you have to modulate that by the heat that didn't flow out from the first two objects. So here's some ideas. You can view a long square cylinder as the combination of two plane walls. You can view a semi-infinite cylinder, so one that's very long this way, but is finite in the other cylindrical direction, as the semi-infinite surface multiplied by the cylinder. And then short cylinder would be the plane wall multiplied by the cylinder. So here you've got the semi-infinite medium, and then a quarter infinite medium, which would be infinite in these two dimensions, but we're looking at an edge. And then you can look at a corner, which is three semi-infinites together. The plane wall, if you were to stop it at one side here, so imagine we're looking at the front of it. So here we're looking inside. Now we're looking at an object which really stops here and kind of conducts inside there. So that's semi-infinite combined with the plane wall. And then quarter infinite would be two semi-infinites combined with the plane wall. Then we've got an infinite rectangular bar, that's one plane wall. Semi-infinite rectangular bar and a rectangular parallelepiped would be combining three plane walls together.